Einstein referred to her as the most important woman in the history of mathematics. Her theorem has been recognized as one of the most important mathematical theorems ever through in guiding the development of modern physics. Yet, many people have not the slightest clue of who this woman was, or what she did that was so significant to our understanding of how our world works. I can only hope I do her memory justice, not just by telling you who she was, but by also giving you an understanding of how her insight led to the coming together of symmetry and quantum theory, pointing academia's arrow toward quantum electrodynamic. Being a female in Germany in the late 1800s was not easy. She was not allowed to register for math classes. Fortunately, her father happened to be a math professor, which allowed her to sit in on many of his classes. She took one of his final exams in 1904 and did so well that she was granted a bachelor's degree. This allowed her to officially register in a math graduate program. 3 years later, she earned one of the first PhDs given to a woman in Germany, and she was just 25 years old. Noether worked at the Mathematical Institute of Erlangen without pay or title from 1908 to 1915. In 1915, she joined the Mathematical Institute in Göttingen and started working on Einstein's general relativity theory. In 1918, she proved two theorems that were basic for both general relativity and elementary particles physics. One is still known as Noether's theorem. Noether's theorem states that every differentiable symmetry of the action of a physical system has a corresponding conservation law. During the 1920s, Noether did foundational work on abstract algebra, working in group theory, ring theory, group representations, and number theory. Her mathematics will be very useful for physicists and crystallographers. Noether's conceptual approach to algebra led to a body of principles unifying algebra, geometry, linear algebra, topology, and logic. 1907 was a very exciting time in theoretical physics, as scientists were hot on the heels of figuring out how light and atoms interact with each other. Emmy wanted in on the fun, but being a woman made this difficult. She was not allowed to hold a teaching position, so she worked as an unpaid assistant, surviving on a small inheritance and under-the-table money that she earned sitting in for male professors when they were unable to teach. She was still able to do what professors are supposed to do. However, in 1916, she would pen the theorem that would have her rubbing shoulders with the other physics and mathematical giants of the era. Noether's theorem seems simple on the onset, but holds a fundamental truth that explains the fabric of our reality. Noether's theorem states that given a physical system, for every infinitesimal symmetry, there is a corresponding law of symmetry. While this requires some parsing, it shows that the conservation of energy and momentum are mathematical consequences of facts that we take for granted. That the laws of physics do not depend on the time or location of the observer. We demonstrate the result in classical mechanics before exploring the theorem in more sophisticated settings.